Yeah.
所以这个已经是希望。
那个学生，我这边系办要签名，然后我会先放在后面，然后刚刚如果没有签的，跟签到是不同章，然后刚没有签的就可以等下下课前去把它签完，谢谢。还没签名的同学，抓紧签名一下，再8分钟。Okay, so let us start today's colloquium. It's give me great pleasure and honor to introduce today's speaker, Professor Stephen Louis.
Professor Louis, as you can see, is currently a professor in UC Berkeley. He received his PhD in physics also from Berkeley in 1976. After that, he worked in IBM Watson Research Center, Bell Lab, and the University of Pennsylvania. And finally, he returned to Berkeley, became a faculty member in 1980, and stayed working there until now. He also a member of Lawrence Berkeley National Lab. His research field spanned a broad spectrum of topics in theoretical condensed matter and also material nanoscience. And his world-renowned condensed matter theory. In particular, he's known for groundbreaking on the ab initio GW method and for his seminal work on surface interface, nanostructure, and reduced dimension. Now, because his outstanding performance, he received many honors. Currently, he's a member of National Academy of Science, American Academy of Arts and Science, and also a member of Academia Sinica, and as well as a fellow of American Physical Society, American Associate for Advanced Science. Now, among his great honor received, I think the most famous one, a few most famous one, I named here, ABS and NISA Raman Prize for Computational Physics, ABS Davidson Germer Prize in Research Society, and the Forsyth Institute Richard Feynman Prize for Nanotechnology. Well, I can continue, but I think I better stop here. So today he's going to talk about fascinating quantum world of atomic thing, one-dimensional and two-dimensional material, symmetry, interaction, and topological effect. Let's welcome Professor Louis.
Well, thank you, Bao, for this very kind introduction. It's my extreme honor and delight to be able to come and give today's colloquium. I think the first time I visit National Taiwan University over 15 years ago, so I'm really delighted to be able to come back today and give this talk. In today's talk, I would like to share with you some of the recent work that we have done in the area of looking at the property of atomically thin one- and two-dimensional materials. In particular, try to understand how symmetry, interaction, and topological effects make this kind of material quite different and fascinating from material that we are familiar with. So as you all know, material has played a significant role in the development of mankind over the history. And we, in fact, have named major periods of our history by materials. For example, starting from the Stone Age, millions of years ago, to the Iron Age, through the Industrial Revolution. And today we are talking about, people are talking about perhaps we're in the plastic age, silicon age, or nano age. And today, when we talk about nanomaterials, we're basically referring to materials that has structure that, at least along one dimension, in the nanometer scale, like nanotubes, copper nanotubes, nanowires, nanoribbons. And then we also have 2D materials like semiconductor quantum wells, graphene, and atomically thin crystals. So in today's talk, I will be mostly focused on looking at 1D and 2D material systems. in particular the optical and electronic properties. So, as many of you may know, atomically 2D materials is a very exciting and popular field nowadays in condensed matter physics. There has been a lot of work in this area, creating a lot of new science and also promises for applications. The most well-known example of this class of material is graphene. Graphite is a layer material. Each layer is made out of carbon atoms in a 2D honeycomb structure. And the layers are very weakly impacting with each other. So you take one of this layer, then you'll have graphene. And because of the symmetry of the honeycomb structure, the low energy electronic states in graphene, in fact, has a very unusual energy versus momentum relation. It behaves like it is a massless direct fermion in 2 dimensions, and that leads to many fascinating properties related to graphene. Of course, graphene is not the only layer material in nature. In fact, there are, well, I forgot to mention, the Nobel Prize in 2010 was given to Dime and Novoselov for their isolation and study of graphene. There are actually many layer materials in nature, hundreds, if not thousands of them. Some of them are superconductors, some are semiconductors, some are insulators. For example, this class of material we call transition metal dichotenides, which consists of layers that has a transition metal atoms in the middle, and then either the trojanide atoms on the top and bottom layers. And this kind of material can be semiconductors, superconductors, metals, or charge-density wave systems. And you have big gap insulators like hexagonal boron nitride, and iron selenide is a very interesting material. In the bulk, it's superconducting, but if you take a single layer of this and put it on top of a surface like strontium titanate, then its superconductor transition temperature can in fact enhance by a factor of 10. And then we also have layer materials which are magnetic. For example, this material is ferromagnetics. And our experimental colleagues have now made single layer or few layer sample of all these materials and able to show that the properties of these materials, when you get down to a few layer level, actually can dramatically change and give you very interesting phenomena. And in fact, because the 2D material are weakly impacting with each other, you could imagine stacking them together, different type of 2D materials, and able to create perhaps new materials with new functionality. So in this talk, I will be as I mentioned, mostly focused on try to understand the electronic and optical property of quasi 1D or 2D and 2D systems. Because of the size and restricted geometry of this kind of materials, their behavior, in fact, are dominated by quantum confinement, enhanced electron-electron interaction, topological, and symmetry effects. This kind of effect often lead to a very new properties and new phenomena that do not exist in the bulk. And often this kind of property can be useful in applications such as optoelectronics. And even more remarkable, as you will see later, the property of this kind of 1D and 2D system can be tuned precisely by gating and environmental screening effects. So here's basically the outline of my talk. I will first talk about a very recent discovery we made. That is, graphene nanoribbons can have novel topological phases that could lead to some very interesting physics. And then the next topic will be to look at the optical and electronic properties of 1 and 2D systems, in particular how electron-electron interaction, band topology, and external screening effects can change their properties. And then finally, if I have time, I'm going to talk about 2D magnetism. Does magnetism exist when you get down to a monolayer of a layer material? And if it does, how does it behave? So let me, since this is a colloquium, I assume that not everybody is in condensed matter physics. So I will begin with some very basic notions about electrons in crystals. Now, this turned out to be impacting a quantum many-body problem because you have approximately 10 to the 22 electrons per centimeter cubed in a material that interact strongly with each other and with the ions. In fact, this is the source of richness of condensed matter physics with many emergent phenomena such as magnetism, superconductivity, and so on. So one needs to use actually many-body techniques to sort of understand the ground state and the excited state or spectroscopic properties of materials. For many materials, with advances in theory and the availability of modern computers, one in fact can now solve this problem from first principles using appropriately formulated many-body theory. And I won't have time to go into this today since this is really not the purpose of this talk, but I will mention some of the results coming out from this kind of calculation. The idea here is to use many-body theory to identify and calculate the appropriate elementary excitations, such as particle-like excitations, electron and holes, or two-particle correlated excitations like exciton, electron-hole pairs, or collective excitation, electron waves, density waves in the solid. Knowing those kind of excitations, then you could try to understand and predict the property of materials. For example, if you look at particle-like excitations, that is the kind of excitation you would get by injecting an electron in a material or extracting an electron from it. This kind of excitation, in fact, are propagating states. The states are extended and propagating, and the states are characterized by wave number k and some other quantum number. And in fact, the amplitude for such excitation, particle-like excitation, is just a phase factor involving k times a function that is perfectly periodic from one unit cell to another unit cell. So if you look at the energy of the electron or hole as a function of k, plotted out, then you have bands. That's the band structure of a crystal. And you could also have gaps existing between the bands. It turns out that if the energy level at which you separate the occupied state versus the empty state is right in the middle of one gap, then you have an insulator. Otherwise, you have a metal. Another thing I want to mention is that because of crystalline periodicity, distinct states exist only in a finite region of K-space. That's called the Brillouin zone. And the Brillouin zone, in fact, is a compact geometric object, manifold. In one dimension, it's just a circle, or a equivalent circle. And then in two dimensions, it's a donut, two torus. And this will be an important concept when we talk about the topology of the electronic state of the crystal. So now let me talk about graphene nanoribbons. And so you take graphene and then you cut out a small ribbon with a width of 1 or 2 or 3 nanometers, but very long along the length direction. Then this is what we call a graphene nanoribbon. Of course, you could cut it in different ways. You could have a ribbon with different width and different edge shape. This is what we call a zigzag graphene nanoribbon because the edge looks like zigzag. And then this is what we call armchair graphene nanoribbon. Now, it turns out that this kind of graphene nanoribbons, in fact, are very interesting. They are all semiconductors, even though that graphene itself is not a semiconductor, it's a semi-metal. And they have very interesting electronic and magnetic properties. When we first studied this kind of ribbons, nanoribbons, this is really an ideal kind of model, a toy model for theorists to play with. And many experimentalists at that time, 2007, think that there's no way you could make this kind of ribbons. However, nowadays, there are really tremendous renewed interest in the graphene nanoribbons because our clever experimental colleagues were able to discover a way to synthesize nearly perfect graphene nanoribbons. And so nowadays, you could get armchair or zigzag or other type of graphene nanoribbon with a width of about 1 to 3 nanometers and length up to several 100 nanometers. And those are synthesized by taking precursor molecules and put it either in a solution or on top of a metal surface. And you just heat it up, of course, under the right conditions. The molecules will polymerize and you will get perfect graphene nanoribbons. And this technique is pioneered by Roman Fasso's group in Switzerland. So you take a molecule like this, you will get a 7 armchair graphene nanoribbon. 7 here refers to 7 rows of carbon atoms forming the width. And taking a bigger molecule, a different molecule, then you can form a 13 armchair graphene nanoribbon. And if you take a molecule with some dopants in it, here is a pair of boron atoms, then you can form a perfectly periodically doped graphene nanoribbons. And all this has been made already. And with other molecules, you could even make ribbons look like this, or several graphene nanoribbons, and putting 2 different types of molecules in your on your surface, you could even form segments of ribbons with different width and forming heterojunctions looking like this. This is something that my colleague Mike Formey had done a few years ago. So now let me turn to topology and then come back to the graphene nanoribbon and look at the electronic properties. So as you learn in math, topology is the study of the global property of an object that is preserved under continuous deformation and characterized by some invariants. So, for example, you could continuously deform this mug into a ball, or continuously deform a mug with a handle to a donut. But you cannot deform a ball into a donut. So topologically inequivalent object cannot be transformed into each other. And in fact, for 2D surfaces, it can be classified, the topology can be classified by integer that correspond to the number of handles here in the mug. So topology is a global property. On the other hand, geometric properties, such as curvature, local curvature, are local properties, but integrals over local geometric properties may characterize the global topology or give you the invariants that characterize the global topology. So a famous example is the Gauss-Bonnet theorem for a closed 2D surface. And you integrate over the Gaussian curvature over the whole manifold, then you always get 4 pi times 1 minus a number. And that number would be 0 if you have a sphere or equivalent of a sphere, and it would be equal to 1 if it's a donut, equivalent of a donut. Now, when we talk about topology of the electronic state of a crystal, we are really talking about the topology of the electronic state over this compact geometric manifold of the Brillouin zone. And the law of local geometry is now taken by a quantity we call the theory connection. It's given by this expression that involves the periodic part of the block function. So once you know the block function, you could calculate the theory connection and therefore the topology of the electronic state. So in fact, the study of non-trivial topology of block bands in the last decade or so has led to a much deeper understanding of many physical phenomena. For example, the existence of protected boundary states, for example, the surface states on topological insulators, the integer quantum Hall effect, and new phases of matters, and so on. And the Nobel Prize in 2016 is given to these 3 gentlemen for their work on basically band topology. Now, in one dimension, that's the case we're interested in for graphene nanoribbons. In fact, you could 1D system can pose topological asymmetry protected topological phases, and this kind of phase is related to